Current regenerative techniques like microfracture are essentially recruiting the right workers, but giving them the wrong instructions. The result is fibrocartilage, a mechanical failure in a load-bearing joint. We must engineer a paradigm shift. Biochemical cues fail because they lack spatiotemporal precision. They are broadcast signals in a dynamic system. We propose a wireless 3D magnetomechanical platform to act as a definitive physical switch. By moving from extracellular scaffolds to organelle-level mechanics, we provide the localized, high-fidelity control necessary to program endogenous stem cell fate in situ. This strategic need for localized control directly dictated the engineering of our multifunctional nanomotor platform, designed to navigate the joint's hostile microenvironment. The so what of our 3D field design is rooted in fluid dynamics. Within the viscous intracellular environment, 2D motion is fundamentally limited by the scallop theorem. By unlocking the third dimension, we achieve a transplanar, rotational bouncing motion. This breaks hydrodynamic symmetry, allowing for a high-efficiency conversion of magnetic energy into mechanical shear. We aren't just moving particles, we are generating high-shear fluid vortices that maximize the mechanical output within the cell while minimizing the required particle dosage. Once internalized by the BMSCs, these nanomotors transition from physical engines to biological programmers. We have redefined the lysosome. In this platform, it is no longer merely a degradative compartment, it is a central signaling nexus. By applying 3D mechanical perturbation, we trigger a controlled lysosomal membrane permeabilization. This mechanical gating forces cathepsin D to leak into the cytoplasm in this neutral pH environment. Cath D undergoes a functional shift, acting not as a protease, but as a signaling molecule that initiates the programming of the cell's fate. This mechanical trigger directly activates the biological machinery required for chondrogenic differentiation. Why 10 minutes of stimulation? Our data shows the 3D mechanical pulse disrupts the actin cytoskeleton, which then requires a full 24 hours to recover. This daily 10-minute trigger is sufficient to maintain a sustained window of SOX9 transcription. By targeting the cofilin actin axis, we tap into the cell's natural mechanotransduction pathways, directing the body's own BMSCs to commit to the chondrogenic lineage with high fidelity. With cellular programming verified, we translated this into a microfracture plus strategy for in vivo validation. This is a microfracture plus strategy. We are no longer limited by the formation of fibrocartilage. By combining the mobilization of native cells with 3D magnetomechanical actuation, we have overcome the primary barrier of conventional surgery. We are wirelessly directing the body's stem cells to build hyaline-like tissue with normal orientation. Our superior ICRS scores prove that this platform offers a clinically viable path to functional joint repair. These results demonstrate the success of the platform and its broader implications for the field of regenerative medicine. In conclusion, we have engineered a high-fidelity toolkit for regenerative medicine. By specifically targeting the lysosome and breaking the symmetry of traditional magnetic fields, we offer a generalized methodology to remotely regulate the mechanical signals of cell fate. This work bridges the gap between nanorobotics and clinical regeneration, providing a non-invasive, wireless future for in situ tissue engineering.